Hello everyone. In this tutorial, we are going to look how to find the radius of curvature at any point on the given function. So now let's understand with the help of this function. I have plotted a one graph. Here I have denoted this graph as a function of x. Here f of x in the form of f of x. Here the f of x may be anything. So here let's understand first of all this graph. So let I have to find the radius of curvature. I have to find the radius of curvature at this point on, on this function. So now what does it mean to radius of curvature? So if let's say if I select this small portion of this curve, let's if I select this portion, small portion of this curve, and if I want to find the circle such that if I draw the circle in this xy plane, then I find in such a way that this circle must touch at this point to this graph. So let's assume it has a suppose let any circle has a center at this point and it has a radius this point to this point. Let's call it r. Now if I draw the circle with this point as a circle and this capital R as a radius, then what I'm getting is just simply circle like this. So it is exactly the pass from this point and it continue like this. So here you can see this circle is touching this point. Let's call it point A. This circle is in touch with this graph at this point A. So now I can say that at this point this function has a radius of curvature. It's r because at this point A, the this curve, this small portion I can I can call it just a arc of this bigger circle. So I can just simply say that this small portion of this curve here very near to this point A, I can just call it the arc of this circle like this, which has radius r. So I can just call it just an arc of this circle. Now in the same way, if I am interested to find the radius of curvature at this point, let's suppose now again let's say it has center here and it has some radius. Let's call it small r. So now let's again draw circle with this radius. So what I'm getting just like this. Again the circle is touching the curve at this point. Let's call it is point D. So now circle is continue like this. So now again this small portion very near to this point D is exactly the same as the arc of this bigger circle with radius this r. So I can draw like this. So I can say that the function at the point D is just simply the arc of this circle radius with radius is a small r. So now how to find this radius in general term? If I have any function, let's call we have I have function y as in y equal to f of x. Now here f of x is just simply the function in terms of x. So it may be polynomial or maybe any trigonometric function or any other function in some in containing only the x variable. So now if I zoom this portion of this curve like this portion, so let's zoom it. So now here in this figure I have just zoomed the previous one very near to this arc. So now when we zoom this first previous figure, we just get here a very big curve because we have zoomed so much. So now just let take any point randomly A and B which are just at some distance. Let's call it at distance del s. So now what we have to do, we have to find the radius of curvature for at this point. So now let's I have drawn the tangent at this at point A. Now in the same way, I have also drawn the tangent at point B. Now at point A, this tangent in this orange color, it's make an angle theta with this horizontal axis. Here I have denoted this. Now it make an theta angle. Now here at point B, again let's draw the tangent at point B. So now again it is for making an angle with this horizontal axis as an theta dash. So now if any function, let's call it is a function f of x. Now the graph of the f of x has any curvature, then if I draw the tangent, sorry, not tangent, but perpendicular at point A and at point B, and if my function f of x has any curvature, then these two perpendicular line are intersect at some point and at some particular distance. So let assume this line from this point A, and which is perpendicular to this tangent. In the same way here B, for B, let's draw the perpendicular and which perpendicular to this tangent line. So here they are making an angle of 90 degree. Here also with this tangent line. So now if my function f of x has any curvature, then these two line, let's call it's AC and CB, must intersect at some point. Here in this case they are intersecting at point C. Now we have to find simply just this distance, and it is just simply nothing but the radius of curvature at this point A. Now remember that mm, the function f of x uh, has different curvature at different point. So what we have to do, we have to just bring this point B very close to this A. So now what we have to do is just limit delta S tends to 0. So now we have to bring this point B very close to the A. So now we can say that this arc here from A to B, this one from this point A to this B, now this arc will be infinitesimally small, very small. So now let's call it ds simply. It is very small, so let's call ds. Now here, if this arc is very small, then also the angle which is made by this two line AC and CB is also very small. Let's call it d theta. Now from the basic concept, we know that the for any circle, for any circle, the simply if I want to find this arc, so I have to just multiply this radius with this angle, so I can find this arc for any circle. So here we can say that this ds is just simply multiplication of this radius r at this particular point. Let's call at r at this point, and this small angle here we have assumed it is d theta. So now we have to find this ds, which is a very small portion of this function f of x. So now what we have to do, so now let's extend from horizontal line from this A, so it look like this. Now also expand vertical line from this point B. So now they are perpendicular to each other. So now if this arc is infinitesimally small, then also the this side of this triangle, which let's call dx, which is also very small. In the same way we can say the vertical line also has a dimension dy. So now here you can see it is the triangle. Let's call it point O. So now O, B and C, it is a triangle, a right angle triangle. So from the Pythagoras theorem, we can say that this arc is forming a hypotenuse. Now here we have considered this arc as a straight line because we assume delta s tends to 0. So we can say it is just simply a portion of straight line. So now we can write like ds equal to just under root of square of this dx So dx square plus simply just dy square. So now we have find out this ds in terms of dx and dy. So now let's write it here. So what we are getting here, dx square plus dy square is equal to r into d theta. So now we can take dx square out from the square root. So what we are getting, let's write it here, 1 plus, now here we are getting dy by dx whole square. Now we have taken out this dx square from the square root. So we simply get dx. On the right hand side we have r d theta already. So now take this dx on the right hand side. So what we are getting, now I am interested in finding the value of r. So I have to substitute the value of this derivative d theta by dx. Now here theta is nothing but just simply look at in the graph here. Theta is just simply this angle which is made by the tangent at this point A with this horizontal, or in the other word with the x-axis. Now here we know from the basic concept of the differentiation that the slope at any point on the curve here, I am talking about this point A. So now slope at this point A is just simply the uh, derivative of this function. Here we have assumed it is f of x. So now we can also say that slope is nothing but simply just tan of theta. So let's write, we can write tan of theta at point A here. At this point we can write tan of theta is just simply del y by dx. Now here we have assumed that f of x equal to y. We have function in the, sorry, y, we have function and we have equate is equal to y. So we can say y is equal to f of x. So now from there we can find the value of this theta simply. So let's apply tan inverse both the side in this equation. So what we are getting, just simply we got the value of theta equal to just tan inverse of dy by dx. Now we got the value of theta. So let's put it here in this equation. So what we are getting, just 1 plus this term in the square root will remain as it is. Now on the right hand side we have r as it is. Now we have to differentiate this tan inverse dy by dx. So now to find the this value of r at any point, we have to first of all determine this differentiation. So now recall the differentiation of simply just tan inverse of x. If I want to find the just differentiation of tan inverse of x, then what I am getting, just 1 upon 1 plus x square. Now here the variable itself is an x and I am also differentiating with respect to x. But now here in my case I have a dy by dx. So I have to use a chain rule for the finding the derivative of this function. So let's do it here. So now take the left hand side as it is, which is 1 plus this dy by dx whole square. Now r as it is. Now first of all let uh, differentiate this tan inverse. So what I am getting is just simply from this equation 1 divided by 1 plus, now I have to square this variable because in this case I have only x. Now I have a function, so I have to square this. So let's square it. Now I have also multiply this with the derivative of this inner function because it is a composite function of this tan inverse and this dy by dx. So I have to use chain rule. So now I have to again differentiate this inner function. It is just simply dy by dx. So now let's Again simplify this, left hand side will remain as it is. Now on the right hand side we have r here. Now we have to again take the derivative of this dy by dx. So it will be the second derivative of this function y, and here y is just our function in terms of x. Y is an f of x. So we have given the uh, equation of the curve. So we just have to take the 2 times derivative. So now we have to find the value of r. So now bring all the terms on the one side and this r on the other side. So what we are getting, just r equal to, now this term and this denominator terms are just exactly same, but here we have power 1 half and here we have power 1. If we multiply this term on the left hand side, then what we are getting, just 1 plus this dy by dx whole square raised to 3 by 2, because we have power 1 half here and we have multiplied with this 1 power, so we get power 3 half. Now we have to divide this whole term with this second derivative, which is just simply d square y by. So that's it. We have find out the formula for radius at this point. So now if we have given the equation which is nothing but simply the y, then we can take the first derivative, and we have to find the we have also have to find this second derivative and just put it here in this equation. And if we want to find at some any particular point, let's say x comma y, then I have to put the value of x and y in this equation. Now simply I get the radius r at any particular point according to my selected point. So now let's go to the figure. So now here in the figure you can see we have find out the this value r in the general form, in the f of x form. Now you can find the radius and you can check it also by plotting a graph on the calculator. Now in the next video, what I am going to do is just simply uh, with the help of this equation that we have derived, this equation last one, uh, we plot two graphs and we can also draw the circle with this radius, and we can we see the how this circle is touching the graph at different points. And thanks for watching this video. I hope you enjoy it.